Hi everyone, today I am going to cover the drag force and terminal velocity. Imagine you have a small spherical object. It's falling through a fluid. Imagine that fluid could be air. If the object is falling down, the air is going to apply a force known as a drag force to it in the opposite direction of the movement. If the object is going down, the force from the air on the object is upward. This force is called drag force, is a type of a friction force. The drag force from the air on the object is proportional to the size of the object. Therefore, this drag force is proportional to the radius of the object. The bigger the object, the bigger the radius, the bigger the force from the air on it. It also depends on the velocity of the object. The faster the object goes, the bigger the drag force would be. Also, the drag force depends on the viscosity of the fluid. If you guys remember, we mentioned the viscosity is coming from the friction between the layers of the fluid. So the higher the viscosity, the higher the friction between the layers of the fluid, the higher the drag force on the object would be. And we also have a constant here, 6 pi in the equation. So if they give you a question regarding a drag force, they would either give you the viscosity is shown by eta here, the radius of the object and the velocity of the object, and they would ask for the drag force, or you will be provided with the drag force, the viscosity, the radius, and they would ask about velocity. So they could give you every parameter except for one, and then you could isolate your equation for the unknown, and then you could sub in your numbers and calculate the unknown. The next thing I would like to talk about is terminal velocity. Let's go back to the object that is falling in the air. I want to draw the free body diagram of this object. I know one force that is acting on the object quite well, and that is the force of gravity, the force from the earth on the object trying to pull it down. That's why the object is falling down. Also, the air applies the drag force, known as F drag. We just talked about it. Also, the air, the fluid, applies a buoyancy force on the object. And as we mentioned previously, the buoyancy forces are always upward. Because at the beginning, Fg, the force from the Earth on the object, is bigger than these two forces, the buoyancy and drag forces, the object is falling down. As the object goes down, its velocity increases. And as you look in here, the drag force is proportional to the velocity. So as the velocity increases, the drag force would increase, such that there will be a point that the net force acting on the object would be zero. Therefore, I could use Newton's law and I can write F net y equals zero. Now, if I write the sum of the forces acting on my object, then I will have the buoyancy force upward plus the drag force that upward and minus Fg because Fg is downward equal to zero. So when the net force acting on the object is zero, that's when the object reaches a terminal velocity. That's when the acceleration of the object is zero, and then the object is moving with a constant velocity known as the terminal velocity. So my goal is to find that terminal velocity. So what I'm going to do here, I'm going to keep the drag force to the left side of the equation, and I'm going to take everything else to the other side. So I have a Fg minus Fb. Now, sub in the equation for the drag force, which is 6 pi eta r vt. Yeah, I'm going to call that v now vt because I have a terminal velocity. That's where the net force acting on the object is zero. And instead of Fg, I can write the mass of the object times the gravitational acceleration. However, I would like to write it in terms of the density of the object times the volume of the object times g, minus the buoyant force, which is the density of the fluid, times the volume of the object displaced, which is the whole volume of the object because all of it is inside the fluid, times g. Now, what we could do here, we could factor out the volume of the object times g. So you have the density of the object minus the density of the fluid. And then on the other side, I still have 6 pi eta r vt. Instead of the volume of the object, I can write 4/3 pi r cubed. I imagined my object is a sphere. So if instead of volume I write 4/3 pi r cubed, that's the volume of a sphere. If I sub that in and isolate my equation, so if I put this in here, and I isolate my equation for v, t little v, that's the velocity. Yeah, if I isolate my object for vt, I am going to have 2/9 r squared g eta, density of the object, density of the fluid, are subtracted in here. So if you're wondering, you have to derive the equation. Not really. The equation is in the equation sheet. Let me go to the equation sheet and let me show you where it is in the equation sheet. The equation is right in here. That's the equation for the terminal velocity. That's when the net force acting on the object is 0. And also the drag force is sitting right in here. What I like to do next is to go over an example I have here for you guys. A sugar granule 1 millimeters across is steered horizontally into hot water and is moving at 1 centimeters per second relative to the t. So I'm going to write down what I have. You're given the radius of the object. This is the radius of the sugar. Yeah, so I'm going to write r equals 1 millimeter. This is not in the standard unit, so I'm going to multiply it by 10 to the minus 3. So I will have that in meters. So I have 10 to the minus 3 meters. You're also given the velocity of the object. So v equals 1 centimeters per second. That is not in the standard unit. So we are going to convert it to meters by dividing it by 100 or multiplying it by 10 to the minus 2. So I'm going to write 1 times 10 to the minus 2. And you're also provided with the viscosity of the hot water. So I am going to write the viscosity as well. So viscosity eta equal 0.547 millipascals times second. So you got to watch for the unit because the unit is not the standard unit for viscosity. The standard unit for viscosity has to be in pascals second. So you need to multiply 0.547 times 10 to the by 10 to the minus 3 to have it in pascals second. So they're asking for the drag force. The drag force, let me grab the equation for the drag force. Drag force equal 6 pi eta r times v. Well, you have everything. All you need to do is just to sub everything in. 6 times a pi, viscosity 0.547 times 10 to the minus 3. Instead of r, for r I sub in 10 to the minus 3. And for velocity, I'm going to sub in 1 times 10 to the minus 2. If we do that, my drag force would be 1.03 times 10 to the minus 7 newtons. And this is as simple as it can get.